Hey everyone, thank you so much for being with us this afternoon. I know it's been a long day of torching and pieing and pie torching, so I appreciate you taking some time out of your afternoon to join us. This talk is called Low Precision Inference Without Quality Loss. That is a little bit of an aspirational title, as you'll see. Let's say it's low precision inference with minimal quality loss. And we're specifically going to be focusing on NVFP4 on Blackwell GPUs. So by way of introduction, I'm Philip, and this is Pankaj. Pankaj is a co-founder at Baseten and leads the model performance team. I lead our developer relations team. Baseten is an inference provider, and so it's a huge focus of ours to be able to take models and run them in production as quickly and as efficiently as possible. To look at our agenda today, I'm going to give you some background on quantization, why it can reduce quality, what model components are safer and more dangerous to quantize, as well as an introduction to floating point and, more importantly, microscaling data formats. That's going to be about the first half of the talk. Then I'm going to invite Pankaj back up on stage, and he's going to give you a deep dive case study into GEMM in NVFP4 on Blackwell. So quantization, what is it? Well, it's basically an extension of something that we've had in the computer science industry for a long time, which is the idea of saving a ton of space by compressing information using fewer resources to represent more or less the same thing. So if you look up here, these are two pictures. One is a max resolution JPEG that I made on my Mac, and the other is I put the slider all the way to the other end, minimum quality JPEG. It's a quarter the size, but to the human eye, it's more or less interchangeable. So the question is, how can we do the same for AI inference? Well, that's where quantization comes in. Quantization is the practice of running inference with lower precision number formats. I'm sure everyone in the room is already pretty familiar with that. So you're probably also pretty familiar with the benefits of quantization. If you're compute bound, if you're doing something like prefill or image generation, you get to use these faster, lower precision cores. If you're doing something that is memory bound on bandwidth, you're going to be able to use less memory back and forth. You're reading less data. This can help with cost, it can also help with scale, and it can help with speed. So quantization is incredibly valuable. However, it can also be pretty risky. So when you run a quantized model, if you see a model out there in the wild that's an FP4, I've seen people on like Reddit and Hacker News and stuff be like, ew, FP4 models, like I don't want to pay for those garbage tokens. And the reason for that is because quantization does run the risk when it goes wrong of reducing model quality. Evaluating quality is a little bit difficult. So AI model behavior is emergent. If you have, for example, a video generation model or a large language model, and you quantize the model, and you look at from layer to layer or weight to weight, you're going to say like, wow, that was a massive amount of loss of precision. Or even my intermediate states, my activations, my hidden states, like these look very different in this quantized model. And so I'm not super confident in the process of quantization. But with AI models, you really have to look at the final output, and you have to determine whether or not the final output has suffered any quality loss. This, in many cases, depends on a few outlier values. So the thing that makes LLMs and AI models interesting to quantize is that not every value is equally important. The importance of weights is not uniform. There's a few outlier values that tend to have a pretty big impact on inference. And the idea is you want to use a number format with a high dynamic range so that you can encode the differences between very small values and the range of very large values so that you're not smoothing over these outliers in either direction. The way you measure quality and the way you figure out whether or not you did a good job of this is basically the same way you evaluate LLMs in general. So for an LLM, for example, you would look at perplexity. You don't want your perplexity to go up. And you would look at your eval benchmarks. You don't want those to go down. For example, a video generation model or an image generation model, you might generate a bunch of scenes at a certain seed and compare them side by side, make sure they look the same. And it's important to double check important areas like function calling and long reasoning sequences and other places that models are capable of going wrong to make sure that your quantization has not affected quality. So Quantization is not this thing that you just take and you just throw it at a model. You don't just take the model, every single number is a 16-bit floating point, and then boom, you quantized it, and now everything is 4-bit. Quantization is much more granular than that, and you can quantize individual components. So some components of the model are relatively safe to quantize. Model weights are just these giant linear layers full of numbers. You can throw those into a pretty low precision format, and not a lot of bad things are going to happen. Activations also pretty resilient, pretty robust to quantization, and it's important to do weights and activations, as Pankaj is going to talk about, because you're going to be doing a lot of matrix multiplication between these two, so they need to be in the same precision. KV cache, we've had a lot of success doing FP8 KV cache quantization. It is somewhat more sensitive to quantization because you have this reuse factor. But overall, KV cache, especially in FP8, has been pretty robust for us for the last year or so. And then attention. Attention is the very dangerous thing to quantize because errors accumulate in attention over the course of inference. So if you have a small issue at the beginning, it can snowball to a massive issue at the end, and that's why attention quantization is one of the most difficult and dangerous parts of quantization. Regardless of what component of the model you're looking at, it's all neural networks, you want to make sure that you're quantizing perhaps with a little bit of granular attention to the layers. The input and output layer of any neural network are going to be more sensitive overall to quantization because they're either accepting and transforming the original input or producing the final output, whereas hidden layers overall tend to be less sensitive to quantization, though that varies on a layer-by-layer basis. So how do we actually start to quantize some of these less sensitive areas as far down as 4 bits? And how do we start to quantize some of these more sensitive areas at all while remaining pretty confident in the overall quality of our model? One answer is this new idea of microscaling data formats, specifically microscaling floating point formats. So if you look at a standard data format, FP16 is going to be what we usually use for unquantized model inference. You have your sign bit, you can't see my mouse, that's all right. You've got the first bit is the sign bit, next 5 is exponent bits, and then the last 10 are mantissa bits. The exponent is what gives you that dynamic range in these floating point numbers. It's what lets you encode both very large and very small numbers. And when you move down to FP8, you are in pretty much the same situation. You still have your exponents and your mantissas. Integer formats are different, though, because you only have the sign bit, and then the rest are integer bits. You only have one number, or like a gap of 1, the whole number 1, in between every single value that you're representing there. So your dynamic range is much smaller. This is why a lot of people's first experience with quantization is in these integer formats, maybe running local inference or running on an older GPU. And these integer formats, yeah, they really hurt model quality. But the floating point formats, as you can see, you're retaining most of the exponent factor, you're retaining a lot of dynamic range. So especially from FP16 to FP8, it works pretty well. The issue is when you try and get to 4 bits, whether you're in floating point or you're in integer. Like in 16 bits, you have 65,000 values that you can choose between. 8 bits, you're down to 256. It's not terrible. Like you can do a lot with 256 different values and a high dynamic range, but it gets tricky. With 4-bit inference, you only have 16 values. You have trillions of parameters in your model, like a 1 trillion parameter model, and you need to use just 16 numbers to represent all of these parameters. It's a little bit difficult. I actually can just show you. This is the entire data format you might be working with. You can fit it on one slide in a slideshow. Like this is maybe not something that is going to be robust enough to scale to high quality inference on a massive model. But there is there's a solution. For every problem, there's a solution. So when we think about quantizing a model, as I said earlier, you don't just take the entire model and chuck it into a quantization algorithm and get out the same thing just in a lower precision. You want to quantize across a certain scale. So for example, in traditional floating point quantization, you might create one scale factor for each tensor. That's the scale factor is what maps you from the original values to the quantized values. So for an entire Q tensor, or K tensor, or V tensor, you're going to create one scale factor. But you can get more and more granular with that. You can go to the channel or even the block level. And that's what microscaling data formats do. So for example, MXFP8, which is a microscaling 8-bit data format, is going to use a block scaling where you have 32 values in a block within the tensor, and your scale factor is computed for just that block. That's going to give you much more granularity and preserve those outliers better for overall better accuracy. It does introduce a little bit of overhead because you now have far more scale factors you have to keep track of and store, but you are much more accurate. And then we can actually take this a step further with NVFP4 in 4-bit. So versus the MXFP4 microscaling format, NVFP4 is NVIDIA's own format. You've got a little bit of difference. The most important difference is that you have a 16 number block, but you also have a second global, which is like a tensor level scaling factor. So you have these two scaling factors working together. This creates far more accuracy, and that allows you a relative efficiency of up to 30% improvement versus the same accuracy created with other number formats. You are still saving enough with this microscaling format that you're able to create more efficient inference. So NVFP4 is a very exciting number format, and Pankaj is going to talk you through how we might apply that to a kernel, specifically the GEMM kernel on Blackwell.
Hi, folks. So yeah, in this talk, I wanted to talk about a practical example. So FP4 is a great format, but how do we practically use it? And I have seen a bunch of talks and write-ups. I feel like they're incomplete. They don't paint the full picture. So that's what I want to do here. Like, how do we use it in production and unlock that benefit? So before we dive into the GEMM kernel, let's talk a bit about Blackwell, which is the first GPU that unlocks NVFP4. Blackwell is the only GPU, the Blackwell B200, that provides NVFP4 computation matmuls right in the tensor cores, right in the hardware. And as we'll see, that is very important. So Blackwell as a GPU is the next generation of GPU. It follows certain trends from before, and I believe like most of us are excited about these trends. So I want to spend like a minute on that. It has bigger tensor cores. If Blackwell is made for one thing, it is bigger tensor cores. Everything, all the new features in Blackwell, almost all the important ones, are meant to unlock the power of those tensor cores. As you might know, the tensor cores are growing in compute power more than anything else in the GPU. And it takes a lot of effort and machinery to unlock that. And I'll talk about those things. It continues the trend of using asynchronous computation. Now, we all know that GPUs are massively parallel machines, not just in number of threads, but each part of GPU can be used in parallel, like the special function unit, the CUDA cores, the tensor cores, the CP async for copying, the TMA for copying. They can all be used together, and you need async compute to do that, right? They need to happen all at the same time. We know that GPUs are good at hiding latency through stalling, through a warp scheduler, but that only gets you to a certain level, and beyond that, you do need async. So all the new APIs in Blackwell, they are async friendly. And it supports lower precision microscaling, which needs to happen in hardware, and which is the topic of this talk. So we need to feed this beast, this tensor core, and we'll talk about how to feed it. So as we'll talk about it more, we'll see all these techniques to unlock it, but why do this? Like, why go to this length and write this complex kernel, thousands of lines of very, very intricate code? Why do it? And the answer lies in these numbers. These are throughput numbers for GEMM across different precisions on the same GPU, the Blackwell B200 GPU. And you can see that the NVFP4 GEMM is about 3.5 times faster than FP16, and about twice as fast as FP8. Now, if you look at these large models, majority of the compute actually happens in GEMMs. And so this factor is huge for any performance engineer. You just can't ignore it, and believe me, you want to use it. Now, one more foundational piece before we jump into the GEMM is let's revisit this NVFP4 format a bit more. And I think Philip explained it very well. but let's just visualize it one more time. So what do we have here? We have only 4 bits for values, right? Now, how that 4-bit works is through smaller block sizes. And with NVFP4, the block size is 16. We have a scale factor for every 16 values. And also notice that the scale factor is also quantized. Scale factor is 1 byte. So imagine these 16 values in 4 bits, they combine to 64 bits. If your scale factor was 32 bits, you're dead. You have 50% overhead. You can't have that. The scale factor is also quantized. It's 1 byte. Relative to MXFP4, the scale is actually precision friendly. We have 3 mantissa bits, so it's not a power of 2 precision. It's not a power of 2, it is fractional, so you have more control over the scaling factor. What you lose is 3 mantissa bits, right? Then your dynamic range goes down, and that's where the innovation comes in, hierarchical quantization. You have a global scaling factor which can take care of the dynamic range, and you're down to a smaller range which can fit with these bits. And like Philip talked about, that's a saving of 30% for the same accuracy, which is huge. So we pretty much do only NVFP4. I think if you're going to use 4 bits, you want to use FP4. If you visualize this picture, this is pretty much compression. Now, Philip gave an example of compression. This is, in a way, compression. What you're taking is taking out common values from a block, pushing them into the scale factor per block, and you're compressing further using the global scaling factor. It's a very nice integrated scheme suited for LLM inference. OK, now let's start going down into the matmul world. And this is what basic matmul is, right? You have a tensor on the left, tensor on the right. You combine them, get the multiplier. With NVFP4 block-wise scaling, it gets a little bit more complex. Now you have scale factors. And scale factors are very granular. Every 16 values have a scale factor. This has to happen in hardware. So this is a picture right from the NVIDIA docs. You have, it's no longer A times B. It's A times scale factor of A times B times scale factor of B. And this all happens in hardware. And we'll look at the details of that. So now, anatomy of this matmul, like how do you use matmul in practice? It's not just the GEMM kernel. You first need to quantize the weights. You also need to quantize the activations, and then you call the GEMM kernel. Any implementation of GEMM kernel, you'll see it takes FP4 input. Where does it come from? You have to prepare for it. You have to set it up. And that's what I'm going to talk about next. And just a highlight of what we're going to talk about, the techniques, TMA, TMAM, and TCGen 05. We'll talk about it. I love to talk about this stuff. I feel like I should say that I am an engineer first and a co-founder second. I love this stuff. GPU writing, kernel writing is the kind of tough problem that you like to solve. We engineers, we want the opportunity, and this is a great opportunity. I didn't plan this, by the way. OK. So back to getting this matmul kernel to work. First thing is that you want weight quantization. Now, as an engineer, you want to use this time that you have very well. The time before the inference is very important. You prepare for it. You quantize the weights offline. You have all the time in the world. You can find the best values of scale factors. You can find the best value of the global scaling factor. You can take the time to find the local scaling factors. And then you have this quantized checkpoint, which is 1/4 the size now, right? Which saves you download bandwidth. It saves you bandwidth space on disk. It saves you space in the GPU memory, which is scarce. And it saves you on the GPU memory bandwidth, which is the scarcest. So a lot of benefit already there. Now, activation quantization. Activation is the runtime value that is coming through the model, and you need to quantize that. Even some part of that can be done beforehand. The global scaling factor, it's for the whole tensor, right? It's a global value. It requires a global reduction. Doing it at inference time will be too expensive. It can be done at the calibration time, though. You just take like a few inferences, like 20 or 30, and you get the maximum value in the tensor, in the activations. And global scaling factor is resilient to that. You can do it offline and store that in your checkpoint. But the activation values themselves, they need to be quantized, right? You need to calculate the local scaling factors based upon the runtime data. That is typically done through an additional kernel, a pre-quant kernel, which is almost like an element-wise kernel, right? The only reduction it does is has to find the maximum value of the 16 block. And that can be done very efficiently with a warp shuffle inside the warp. So you're not going back to the global memory or the shared memory. So it's a very, very fast kernel. It does add some overhead. In practice, we find that it adds about 10% overhead to the GEMM kernel. But the GEMM kernel is 3.5 times faster, or twice as fast as FP8, so you still benefit a lot. And it can be optimized. Like, it's just very hard. The GEMM kernel, as we look at, is already very, very complex. So merging this part into the GEMM kernel is not straightforward. But I wouldn't be surprised if somebody does that in future. Maybe one of you guys can do it. So let's look at the data flow of this GEMM kernel now. Like, the heart of it is the TCGen 05 operation. We'll talk more about it very soon. The data flow is that your data, your activations and weights and their scale factors are in global memory, right? The kernel always starts with the global memory. This has then to be copied into the shared memory. You use TMA to do it very, very efficiently. Now, scale factors, TCGen requires scale factors to be in this new form of memory called tensor memory that we'll talk about. So you need to do that copy, get the scale factors into the tensor memory, and then you do the matmul using the TCGen 05 operation, which writes the output into also tensor memory, which is called the accumulator. It's called the accumulator for a reason, because matmul is not a one-shot operation. You are iterating over tiles of A and B to get the final output. You do this accumulation over a period of time. And that's actually very, very important, as we'll look at shortly. So now this matmul output is in tensor memory. Tensor memory is not general purpose. You need to copy it out first to the register memory, and then you can do post-processing on top of that. And we'll talk about that. And then you have the output. Now, there are some salient features in this diagram. One is the pipelining. This is all very, very incremental. All the pieces are actually working together at the same time. While the TMA copy is happening, the MMA is working on a different tile, and the epilogue is working on yet another tile. And we keep the whole pipeline busy throughout. And this is extended further with persistent kernels. Instead of launching kernel for each output tile separately, we run some persistent kernels that occupy the whole GPU, and they keep processing different work tiles. So you avoid the kernel launch overhead, but you also benefit from this pipelining being extended to more pieces of work. You can keep the pipelines busy. You want to make the best use of your GPU. Now we'll start getting down into the technology pieces which are required to unlock this tensor core. Like I said, this tensor core is very, very powerful, and it's a lot of effort to do it. And the one key technique is TMA, which is basically hardware-based copy. You use the hardware to do the copy from global memory to shared memory. Global memory is the most scarce. That bandwidth is the lowest in the GPU, so you want to use it well. And TMA allows you to completely offload that to hardware. It requires only one thread to start the TMA operation, and you just describe your operation using a descriptor. So one register, one thread. That's all it needs, and you can kick it off and wait for the results using an asynchronous barrier. So completely offloaded to hardware, and not just that, it supports multicast. So you get the data from global memory down to L2, down to the shared memory of multiple CDUs, not one. Why does it matter? Because GEMM kernels have this structure. Like your A and B tiles are used for not just one output tile, but many. So this is a natural thing that happens in GEMM kernels, where the data needs to flow into many CDAs. And by doing this, you're copying once from global memory and L2, but propagating to multiple shared memories. So very important. And swizzling, like we know, shared memory is a bunch of banks. It's basically 32 banks, which can all work in parallel, but one bank can do one thing at a time. So you want to spread out your values. You need to do this swizzling, which you almost always do, and TMA does that in hardware. TMA does a lot more, but in the interest of time, let me move on. TCGen 05 tensor core generation 5 is the instruction that does this work on Blackwell. So Volta, Turing, Ampere, Hopper, this is the fifth. This is the Blackwell tensor core generation 5 instruction, a modern instruction, also meant to offload your work completely. So this again works with descriptors. You keep your data in shared memory and tensor memory. You describe the work. You actually, for the first time in the history of tensor core operations, you don't pass any operand data directly through thread registers. There is none of that. You describe your operation, you shoot it off, and then you wait it for asynchronously. What that does is that, like TMA and now this MMA, it frees up your threads and registers to do other stuff. And it's very, very common to combine GEMM operation with others. The attention kernel is actually GEMMs combined with softmax, right? There are two GEMMs combined with softmax. So you need that extra processing power, and this instruction allows you to do that. It also supports microscaling, which is critical for this use case. Now, tensor memory is a new kind of memory. You can think of it as register memory, which is dedicated to tensor cores. Now, like I said, Blackwell is focused on tensor cores. This is dedicated memory for that. And this frees up your regular registers for doing other stuff. It helps you reduce register pressure so that you can do more things. What you free up all of this stuff for the epilogue. Epilogue is where you need to decoint. You need to combine your global scaling factor back. You can do fusions. We found that you can fuse GELU and ReLU and SILU into the GEMM kernel and do more other stuff. And it also helps you reduce. One small tip is that you can use tiling to do epilogue and increments, and then that saves you register pressure. I think I'm almost out of time, so I'll just say like one sentence about CDA pairs. Another technique that is required to unlock the power of these tensor cores, where you can pass data through 2 CDAs to this big tensor core and get 4 times the compute out of twice the data. So your arithmetic intensity increases. And I think I'm really out of time. So
yes.
hand it off.
Thank you so much, everyone, for being here and sticking with us through this. Quick shout out to K Bao, kernel engineer on our team, who did a ton of work on this gem for us. You can connect with us on LinkedIn and Twitter on the QR codes here. We're also going to be downstairs at the Baseten booth. If you want one of these awesome shirts, or if you want a job on the model performance team because you think this stuff is the coolest thing ever, come say hi to us. We'll be right out there answering questions before the next talk, and then we'll head downstairs. Thank you so much, everyone. Have a great day.
Thank you so much.